Hi, my name is Noam Buckman, and I'll be talking to you today about our work on generating visibility-aware trajectories for cooperative and proactive motion planning. And the motivation for this work is the reality that nobody on the road has perfect perception. This is very clear, for example, with blind spots. As vehicles on the road are traveling, they're going to have regions where they'll have very limited visibility. And as we are trying to create safe trajectory planners for autonomous vehicles, we need to be able to plan considering the fact that the vehicles around us may have these blind spots and limited visibility. If the vehicles around us don't know where we are, they might take actions that lead to collisions. So in this problem, we'll be considering an ego autonomous vehicle that has to execute some high-level traffic maneuver. For example, we have here this green car that needs to execute a lane change, depicted by this dashed line. Typically, we'll consider the vehicles around us for doing collision avoidance. However, in this work, we'd like to go one step further and consider the fact that they will have blind spots, and the vehicles around us may lose track of us as we enter these blind spots. And the goal of our ego vehicle now is to be able to come up with trajectories that minimize the perceptual uncertainty as it executes this traffic maneuver. Now, there's been multiple approaches to try and tackle this problem. On one end of the spectrum is a geometric approach, which considers minimizing the geometry itself of the blind spot without necessarily considering how the vehicles around them are doing the estimation. Another approach is risk-aware planning or using reinforcement learning to come up with policies that can work even in scenarios where it has limited visibility. However, here does not directly model the blind spot. In robotics, belief-based planning introduced the idea for a single robot to do both estimation and control in scenarios with limited observability. Similar ideas have been used in multi-robot settings, such as in active formation control. However, here the estimation and control are assumed to be jointly being done by all robots in a centralized manner. In our approach, we're going to combine both trajectory optimization with belief space planning in what we call visibility-aware trajectory optimization. And there's 4 steps to this approach. First, we're going to generate multiple candidate feasible trajectories that our ego vehicle could execute. Then, for each one of these trajectories, we're going to compute an uncertainty metric that captures how visible each of these trajectories are. Then, for each one of these trajectories, we're going to associate a visibility cost that actually scores these trajectories. And finally, we're going to choose and execute the minimum cost trajectory from all of these trajectories. So we'll start first with how we generate those candidate feasible trajectories. Each candidate trajectory is going to be parameterized using the Frenet frame, where each point along the trajectory is parameterized by a deviation off of the center line d and a longitudinal deviation s. Multiple trajectories can be generated by deviating the final position of each of these trajectories. For example, we can vary the final lateral deviation and longitudinal speed to generate multiple candidate trajectories. Each of these we can then check for kinematic feasibility and that it's collision-free with the surrounding vehicles. Then we're going to model the visibility of these vehicles using the extended common filter. So we assume that the vehicle around us, here this red vehicle, collects measurements yj of the ego vehicle's position and computes an estimate on the ego vehicle's position xi hat. Then the measurement's noise is going to depend on whether it's in the blind spot or not. When the ego vehicle is in the blind spot of the surrounding vehicle, it gets an infinite noise measurement, whereas when it's outside of the blind spot, it gets some noisy measurement with some variance RC. Now that we have a model for how the surrounding vehicle is collecting its estimate on the ego vehicle, we can then compute that estimate covariance for every point along the trajectory using just out-of-the-box extended common filter update. Now we have the dynamics of the estimate covariance representing the uncertainty of the surrounding vehicle on the ego vehicle for each of these trajectories. Next, we'll need a cost for each of these trajectories. We'll start with a baseline trajectory cost that penalizes the jerk on the deviations from the center line. This represents the comfort to the driver of each of these trajectories. There'll also be terms representing the amount of time it takes to traverse the trajectory and the final deviations off the center line. One of the results from trajectory optimization is that quintic polynomial trajectories minimize these types of costs. We then propose a visibility cost that gets added to this baseline trajectory cost, which will be a function of the estimate covariance from the extended common filter. This will be weighted by a visibility cost weight, Km, which represents the importance of the visibility to our trajectory optimization. We propose two types of visibility costs. The first is a mean variance cost, which penalizes the average covariance along the entire length of the trajectory. The second type is the terminal variance cost, which only penalizes trajectories that have high covariance at the end of the trajectory. And this is especially important for scenarios where we know that the ego vehicle and surrounding vehicles will interact towards the end of the trajectory. For example, when trying to overtake another vehicle. Now that we've scored all of our candidate trajectories, we choose whichever trajectory provides us the minimum cost with both the baseline and visibility cost. So I'm now going to show you some of our results in 3 different scenarios where this can be applied. The first is an overtaking maneuver. So here we have an ego vehicle that's changing lanes into the blind spot of a lead vehicle, here depicted in red, with 2 blind spots on either side. So first we'll take a look at the estimate covariance as the ego vehicle executes a trajectory. So on the left, once it enters the blind spot, our estimate covariance grows and shrinks once it exits that blind spot. On the right, we can take a look at this covariance for different outputs of our algorithm using different weights, Km for the visibility, and also which type of visibility cost, whether it's mean or terminal. We can see that for higher visibility weights, we get lower covariance along those trajectories. Here, for example, are outputs for different weights. On the left, we have the mean variance cost, where we can see as we increase that Km, the ego vehicle is going to try and push out of the blind spot and maximize the number of measurements it gets. We can then study how our algorithm performs with different traffic maneuvers. So we do this by varying the initial and final positions of the traffic maneuver trajectory. So this is different parameters of the actual lane change. On the left, the baseline cost is plotted. As we increase on the horizontal axis the visibility weight, we see that the comfort and performance of our trajectories increases. And on the right, we plot the actual visibility cost, and we see that as we weight the visibility more, we see a reduction in the covariance cost, showing that we're providing more importance towards the relative visibility of each of these trajectories. A second scenario we look at is a braking scenario, where now our ego vehicle needs to stop behind this lead vehicle shown here in black while considering the blind spot of this red vehicle. And here the variance is going to depend on how long it takes to enter that blind spot, and also the speed at which it enters that blind spot. On the left, we see the visibility aware trajectory for a weight equal to 1. And on the right, we increase the weight tenfold and show that the visibility aware also comes up with a trajectory that tries to maximize the amount of time it is visible to the other vehicle. And you can see that we have a varying amount of deviation from that baseline, showing that we can tune this parameter to get the desired amount of responsiveness to the visibility aware planner. Finally, we can look at an occluded intersection. So here we have an ego vehicle that's approaching an intersection, which could be a very dangerous scenario, especially if we have cross traffic. So what we do here is the ego vehicle is going to simulate cross traffic, here depicted in this light pink box, and models the blind spot due to this bush. And now, using a similar planner, the ego vehicle will deviate from its center line to ensure that it maximizes its visibility before entering the intersection, trying to maximize its safety as it enters this high-risk area.